Greetings and welcome to GILFORD'S lectures. So today we are going to be looking at an Htttc electrostatics exam question which was written on January 21st, 2022. The very first exercise of that exam question goes to us. Express the velocity v and the acceleration a of a particle in cylindrical coordinate. Let's look at the solution. The very first thing to recall here is that the unit vectors in Cartesian coordinates are given by ex, ey, and ez, while er, e theta, and ez are the unit vectors in cylindrical coordinate. Remember that the position vector of a particle in the Cartesian coordinate system is given by r vector equals x e to the x plus y e to the y plus z e to the z. Differentiating this position vector with respect to time, you obtain the velocity vector, and the second derivative of the position vector with respect to time, you obtain the acceleration vector. So now, let us draw out a schematic diagram for the coordinate systems in question. It is important for you to know that though the question asks us to get the velocity of a particle in cylindrical coordinate system, we'll actually be embedding our cylindrical coordinate system on the Cartesian coordinate system. For you to be able to do that, you must first of all start by drawing your Cartesian coordinate system where your coordinate axes meet at the common point O. Along the z direction, we have the unit vector Ez. Along the y direction, we have the unit vector Ey. And along the x direction, we have the unit vector Ex. This is the particle m for which we are interested in getting its velocity in cylindrical coordinate system. This particle m has a reflection m prime on the xy plane, and the distance from m prime to m is given by z, and the unit vector in that direction is given by Ez. The distance from the point O to the point M prime is given by r, while theta is the angle made by r with the positive x-axis. The unit vector along the r direction is given by er, while the unit vector along the direction of increasing theta is given by e theta. This line represents the vector OM, that is the vector from the origin to the point M. This other one represents the vector OM prime, while this other line represents the vector M prime M. And as you can see, OM prime vector plus M prime M vector is equal to the OM vector. So now, let us have a projection of our xy plane. From the three-dimensional figure above, we get the xy plane below. Remember that we want to project the xy plane from the three-dimensional figure we are above. So for you to do that, you must first of all start by drawing your coordinate axis, where this is your x and this is your y axis, which meet at the common point O. This distance is the distance r, and it is the distance from the point O to the point M prime. And theta is the angle made by r with the positive x-axis. This line represents the unit vector in the x direction, Ex, and this line represents Ey, which is the unit vector in the y direction. Er is the unit vector in the direction of r, and the angle made by Er with Ex is theta. And why is it theta? It's simply because this angle and this other angle are corresponding angles, and we know that corresponding angles are equal. The unit vector in the direction of increasing theta is given by E theta, and it makes an angle theta with the unit vector Ey. We know very well that this other angle and this other angle are corresponding angles, but we may not have a direct relationship between this angle here and this one here. So how do you get this angle theta? Observe that the unit vector Ey and Ex occur at 90 degrees to each other, that is pi on 2. Also, the unit vector E theta and ER also occur at 90 degrees to each other, that is pi on 2. It therefore means that this angle is the angle pi on 2 minus theta. And let's assume that we don't know that this angle is theta, so let's call it a certain x. Since E theta and ER occur at 90 degrees to each other, it therefore means that the sum of x and pi on 2 minus theta equals pi on 2. You discover that this pi on 2 cancels out with this, which therefore means that x is equal to theta. That is why we have theta as our angle here. So now, considering just the section with the unit vectors in the projection of the xy plane above, this is the figure we obtain. Observe that in this figure, the unit vectors ER and E theta vary as theta varies. That is, if you increase theta, E theta will also change its direction, and if you decrease theta, E theta will also change its direction. Let's assume that you have chosen to increase theta. So increasing theta, you observe that E theta is going to move in this new direction. So you have your E theta rather here when you increase theta, and if you decrease theta, you observe that your E theta is also going to move in this new direction. So you have your E theta here. The same applies for ER. Also, observe that ER and E theta could be resolved along the horizontal and the vertical component. So let's start by resolving the vector ER, that is the unit vector ER, along its horizontal and vertical component. So if you resolve the vector ER, you are going to obtain EX unit vector cos theta plus EY unit vector sine theta. Also, if you resolve the vector E theta, you are going to obtain negative EX unit vector sine theta plus EY unit vector cos theta. So those are the two expressions you obtain. These expressions below actually corresponds to these expressions above. Now, you may ask yourself how you can represent the variation of E theta and ER with respect to theta mathematically. For you to do that, you simply write it as such: the differential of E theta d theta exists. That is what it means for E theta to change as theta changes. Also, the differential of ER with respect to theta exists. That is what it means for ER to also vary as theta varies. These are very important expressions, as we are going to see in our calculations. So now, the above figure enables us to get a convenient relationship between the unit vectors and the angle theta by simply resolving ER and E theta. When we did resolve ER and E theta along its horizontal and vertical component, we obtained our ER to be equal to EX cos theta plus EY sin theta, and our E theta to be equal to negative EX sin theta plus EY cos theta. So differentiating ER and E theta with respect to theta, we obtain, so we start by differentiating our ER with respect to theta. So when we are differentiating this expression, our ex and ey is going to be constant. They're actually constant because they are not functions of theta. The only functions of theta we have here are cos and sine theta. So when you differentiate your er with respect to theta, you obtain negative sine theta when you differentiate cos theta, and you obtain cos theta when you differentiate sine theta. So you obtain negative ex sine theta plus ey cos theta when you differentiate your er with respect to theta. You observe that this expression is actually equal to e theta. That is why we say that this implies the derivative of er with respect to theta equals e theta. Similarly, when you differentiate e theta with respect to theta, you are going to obtain negative cos theta. So your negative sign is maintained, your ex is a constant, it's maintained, and your sine theta when differentiated gives cos theta. And when you differentiate cos theta, you obtain negative sine theta. And this implies the derivative of er with respect to theta is equal to negative er. So it is actually equal to negative er because if you factor out your negative sign here, you are going to obtain ex cos theta plus ey sin theta, which is equal to er. So this expression is actually equals to er, and you attach a negative sign. So now let us remember that Newton's dot notation depicts the differential of a dependent variable to time. We should therefore know that theta dot equals d theta dt and theta double dot equals d theta dot dt. Also, arrow dot equals d arrow dt and arrow double dot equals d arrow dot dt. Recall that for you to get the velocity of a particle, you must first of all get the position vector of the particle and proceed to the first time derivative in order to get the velocity. So now, as we saw on the 3D diagram, the particle has position vector OM vector. Remember that the distance OM prime is equal to R and M prime M is equal to Z. Assigning the unit vectors, we get the vectors OM prime vector to be equal to RE to the R and M prime M vector to be equal to ZE to the Z. Now, OM vector equals OM prime vector plus M prime M vector. So we are going to replace for OM prime RE to the R and for M prime M ZE to the Z. It therefore implies that we obtain OM vector to be equal to RE to the R plus ZE to the Z, which is the position vector of the particle. Now, differentiating the position vector OM vector with respect to time gives us the velocity of the particle in cylindrical coordinate. So when you replace OM with the expression for its position vector, you are going to obtain this expression. We know that the differential is distributive over addition, and so we are going to obtain the expression below. By product rule of differentiation, you are going to obtain the differential of OM vector with respect to time to be equal to this expression. So, for you to be able to obtain this expression, you simply start by holding arrow constant and differentiating the unit vector ER with respect to time. And when you do that, you also hold E arrow constant and differentiate arrow with respect to time. Then you move to the second expression where you hold Z constant and differentiate the unit vector EZ with respect to time, and hold the unit vector EZ constant and differentiate Z with respect to time. So now, if you observe the expression of the derivative of the OM vector with respect to time, you are going to observe that the very first term in that expression was divided by d theta both in the numerator and the denominator. I know you are going to ask yourself, why divide both the numerator and denominator by d theta? To answer that question, let's first of all recall that the differential of e theta d theta, or with respect to theta, equals negative er, while the differential of er with respect to theta equals e theta. Also, from the Newton's dot notation, we have our theta dot to be equal to d theta dt, our theta double dot to be equal to d theta dot dt, our r dot to be equal to dr dt, and our r double dot equals dr dot dt. So when we divided the very first term by d theta both in the numerator and denominator, in essence we wanted to obtain this expression which corresponds to this, that is d theta dt, and we know that the expression is equal to theta dot. Also, we wanted to obtain this expression which corresponds to this expression and is equal to e theta. And here we already had dr dt which corresponds to this dr dt and equals r dot, and here we already had dez dt, of which you know that our ez is a constant and the differential of a constant with respect to time equals 0, and here dz dt, we already had that expression, and we know that from the Newton's dot notation that expression is equal to z dot. So we divided only the first term both in the numerator and denominator by d theta, so that we are going to obtain this expression and this. We didn't divide all the other terms because we already know what the differentials of the dependent variables there are going to give us. So essentially, you are going to obtain the derivative of OM vector with respect to time to be equal to r theta dot. Remember that your d theta dt equals theta dot, and your der d theta equals e theta. So that's why we have e theta here, and this expression here is equal to r dot from the Newton's dot notation, and your er is maintained, while the derivative of ez, which is a constant, gives 0, and when multiplied by z it still gives us a 0, and the derivative of z with respect to time from the Newton's dot notation gives us z dot, and our ez is maintained. And so this is the final expression of the velocity of the particle m in cylindrical coordinate. So we have finally come to the end of our video. I hope you loved the presentation. If you did, please subscribe and give me that thumbs up. So thanks very much for watching GILFORD'S lectures, and please do not leave without subscribing.